Okay. Okay, so good afternoon, everyone. We will start exploring lecture 6. Finally, get into the Fourier transform. So in the lecture 5, we talked about the Fourier series. And this Fourier series is works for periodic signals. And in particular, we talk about periodic continuous time signals, xt, and also periodic discrete time signals, xn. For both classes of signals, we can represent this, we can decompose these signals in the Fourier domain and represent them using the Fourier series. And in particular, for the continuous time periodic signals, we need to use a infinite collection of Fourier eigenfunctions to represent the signal. But for the discrete time periodic signals, we only need to use a finite number of Fourier eigenfunctions to represent signal. So that is the difference between these two classes of signals. So of course, the common feature for these two classes is that they are all periodic signals. So a very natural question is what should we do for aperiodic signals? Because most of the signals that we deal with in practice are aperiodic signals. So this is what we are going to explore in the lecture 6. We are going to talk about the Fourier transform, which is specifically designed to deal with, to represent aperiodic signals in the Fourier domain. So we can start with this thought experiment with this motivation. Now suppose that we are looking at a signal xt. Now here we always start with continuous time signal, and later we will discuss discrete time. Now let's suppose we have a continuous time signal xt which is not periodic. Right? So it is a general signal, not periodic. Now, the question is, how can we increase the flexibility of our spectral representation in order to model these more general signals? So in this case, we cannot, okay, so there are two questions. In this case, can we still apply the Fourier series to represent these aperiodic signals? Now, if not, what will be the challenge? What is the issue here, and how can we resolve that issue? Okay, so let's look at this simple example. We can compute the Fourier series as if xt was periodic with period t by using the values of the signal on the interval. So basically, if you recall that in the Fourier series, we have a formula for calculating ak. So ak is 1/t0 integration over one period of the signal, and it's xt e to the power of negative j k omega naught t dt. And this formula applies to periodic signals. In particular, these two, E naught and omega naught, they all depend on the underlying fundamental period of the signal. However, now we are dealing with a aperiodic signal, so it does not have a specific period. So, but we can still try to apply this formula and calculate the Fourier series representation for this signal. And the key, the challenge here is that it does not have a period. So what do we do? Well, a very simple idea is that since the aperiodic can be equivalently understood as the period is actually infinity, so that you don't actually have a finite fundamental period. So what we can do here is that we can follow this, we can still calculate this Fourier series coefficient AK as if the signal has a certain fundamental period T naught. So we are going to take integration over one period. And then we push this period to infinity. And in that case, letting t goes to infinity, meaning that this signal actually does not have any does not have a finite fundamental period. So it is actually a periodic signal. Okay, so we can do this in two steps. Calculate AK for a specific fundamental period T naught. And then the second step is to push this fundamental period to infinity. So we can use this rectangle signal as a specific example. In the previous lectures, we talked about periodic rectangle signals. For that signal, we can do Fourier series transform. But now for this rectangle signal, it is aperiodic. It only has one rectangle part between negative half and half. The amplitude is constant 1. So this is a aperiodic signal. Okay. Now let's try to calculate its Fourier series following this idea. Okay, so we can set a t that is, we can pick a period that is bigger than the interval that covers the interval negative half and half, so that plugging this into the formula for AK, we have 1 over t. Now the integration is over that period, but since the signal has non-zero values only between negative 1/2 and 1 over 2, so the integration actually takes place over this fixed interval. So integration, now xt is the constant 1, so it is omitted here. So 1 times the exponential part is e to the power of negative j k omega naught t dt. So this is exactly following the formula for the Fourier series. And in particular, this omega naught is 2 pi over this fundamental period, capital T. And later on, we are going to push it to infinity. Now, evaluating this integration, we end up and simplify. Okay, once you evaluate this integration, you need to deal with 2 complex exponentials, and then you can use Euler's formula or inverse Euler's formula to simplify it. the complex exponentials into sine and cosine signals. Okay, after simplification, you end up with this result. And in particular, we'll define a very special function called the sinc function, which is sine pi t over pi t. And we will see these functions later on many times because it is highly related to the spectrum of the rectangle signal. So this is just a definition. By introducing this sinc function, now this result is essentially the sinc function evaluated at k omega naught over 2 pi. Because essentially you just let the argument within the parentheses, letting this one equal to pi t, and then you can tell that this t is k omega naught over 2 pi. So what do we get? Oh. So up to now, we found that for this rectangle signal, the Fourier series, now assuming that setting the fundamental period greater than no. Okay, let's call this fix a fundamental period, capital T, and we just shown that the corresponding Fourier series is given by 1 over T, capital T, and the sinc function evaluated at k omega naught over 2 pi. Well, omega naught is 2 pi over T naught. And in particular, for this sinc function, you can use MATLAB to visualize this function. It looks like this. So it's exactly the sine function because the sine function is in the numerator. Of course, we have a time scaling factor pi here. So the axis is squeezed by the factor pi. But it is essentially the sine function. So you can see there's a sort of a sine wave here. Now the amplitude of the sine function is scaled by 1 over pi t. So as t gets bigger and bigger, the amplitude becomes smaller and smaller. So that's why the amplitude decreases as t deviates from 0. Okay, so this is our result. And then we said that because in this case, xt is actually not periodic. So the actual period is actually infinity. So we'll let t goes to infinity. Okay, let's stay on this page. So if we let t goes to infinity, we can see that this coefficient ak, for this coefficient ak, the amplitude 1 over t naught, this part will goes to 0. Okay, this is clear. However, we have this sinc function part. Now, from this picture, or from the definition of the sinc function, we can tell that because it is sine something divided by pi t, so letting t goes to infinity we can see that first of all, the entire sinc function is bounded. It's between 1 and negative something. So the entire amplitude, the value of the sinc function, the range for the sinc function is bounded. So this part is bounded no matter what value we are looking at inside the argument. So there's a bounded number divided by capital T naught, and this capital T naught goes to infinity. So we conclude that AK actually goes to 0 for OK. So which means that if we increase the fundamental period, then all the Fourier series coefficients, they actually goes to 0. They keep decreasing, goes to 0, which makes this representation meaningless, because in the end, you always get 0 result. So this is the issue of directly applying Fourier series to represent aperiodic signals. You always end up with a 0 representation, which is meaningless. And this is an illustration of the spectrum AK when this fundamental period keeps increasing. So at the very beginning, we can have, we start with a finite fundamental period, and then we can evaluate this AK. So it is basically a scaled sinc function. So in the end, the picture for the AK, so the amplitude for all the AK, they look like this. It's a sinc function. As we increase the fundamental period T, increase it to 2 or to 4, or keep increasing, we can see that this sinc function, this entire sinc function is going to be scaled by a diminishing factor 1 over T, so that the entire spectrum is going to compress. So in the end, as T goes to infinity, this spectrum will converge to a 0 spectrum, which is meaningless. But at the same time, you can see that if we increase the fundamental period T, the spectrum is actually denser. This is because in the AK part, we have K times omega naught. This part, which is K times 2 pi over T naught. So if we increase the fundamental period, the resolution that we are looking at in the spectrum domain is actually higher and higher, because the resolution is 2 pi over T naught, right? This fundamental angular frequency is becoming smaller and smaller. So which means the resolution of the spectrum is higher and higher. So that's why, so we have two effects here when we increase T. One is that the resolution of the spectrum keeps increasing. So the spectrum is more and more continuous, because we have more and more discrete points over this entire spectrum domain. However, at the same time, all the amplitudes of the spectrum are decreasing. So in the end, they converge to 0. Okay, so this is the issue when we apply Fourier series to represent, to analyze the aperiodic signals in the spectrum domain.
That's a quick question.
Yes.
So is it correct to say that we still have the spectrum, but it converges to 0, and that's why we can't?
Yes. So you can see from these pictures, right? As for every finite value of capital T, we can indeed draw a spectrum. But then, because this is an aperiodic signal, so the period, right, is not finite. Period goes to infinity. But when we goes to but when we let capital T goes to infinity, the spectrum actually diminishes to 0, and that conveys no information to us.
Okay.
So the idea is to somehow get rid of this. Now the issue is caused by this coefficient 1 over capital T in the induced in the Fourier series formula. Right? This part is introduced in that formula for calculating AK. However, in this case, it is this coefficient that causes the spectrum to vanish in the limit. So the idea is to get rid of this coefficient, and then that naturally gives us the definition of Fourier transform. So the Fourier transform is introduced to describe the limiting behavior of the picture that we just discussed. And instead of looking at AK, because we just shown that as t goes to infinity, AK goes to 0, which is meaningless. So instead of looking at AK, we look at t times AK, so that now this 1 over t can goes away. And when we look at t times AK, so we can draw it. Let's write it down here. T times AK is actually T naught times AK is actually this sinc function, K times omega naught divided by 2 pi. So it is just this sinc function. And moreover, as we let T naught goes to infinity, as we discussed, for this part, the resolution keeps increasing and increasing. In the end, the spectrum in the limit, the spectrum becomes continuous. So in the limit, we can say this simply reduces to instead of looking at these discrete points in the spectrum domain, we are looking at a continuous variable omega in the spectrum domain. So which means that if we only look at the envelope of the Fourier series spectrum, then this envelope, capital T times AK, it is meaningful. And then for this rectangle function, the limit of this envelope is simply the sinc function. Therefore, to summarize what we just did, we first applied this Fourier series formula to analyze the aperiodic signal. And then we found that, okay, this coefficient 1 over t causes the spectrum to vanish in the limit. And then to resolve that issue, we simply move this capital 1 over capital T to the left of the equation. So we look at capital T times AK. And then capital T times AK simply reduces to this integration. Right? And then for this integration, we let capital T goes to infinity. And you can see that this integration will become this the following integration. So the integration is now over the entire domain, time domain, because we let t goes to infinity. And moreover, here this k omega naught. Now in previously, k times omega naught is like the discrete points that we sampled over the spectrum domain, in the spectrum domain. However, once we let t goes to infinity, this sampling becomes denser and denser. So in the end, we just need to look at this omega in the continuous spectrum domain. And then this defines the Fourier transform. So we given a signal xt, the Fourier transform is denoted by capital X j omega, given by this integration. And what is special here, different from the Fourier series, right? Here omega is a continuous. So this omega is any real number. So it is continuous frequency domain. But in the Fourier series, when we deal with periodic signals, recall that the spectrum AK is always discrete. Okay. And now when we deal with aperiodic signals, the spectrum is always a continuous spectrum. So here's a more formal definition of the Fourier transform. So we have the Fourier transform and the inverse Fourier transform. If you look at the Fourier transform, it is actually, the underlying idea is exactly the same as the Fourier series. So we can, this is basically, projecting the signal onto each of the eigenfunction e to the power of j omega t. Now this is a standard eigenfunction in the Fourier domain. So we are calculating the dot product between the signal xt and this eigenfunction. And mathematically, this, as we discussed before, this dot product is mathematically defined by that integration. So this Fourier so the underlying geometrical picture is the same. We are projecting the signal of interest onto a set of eigenfunctions in the Fourier domain. But what is different here is that in the Fourier series, to deal with periodic signals, we only need a discrete. It's infinite. It is still infinite, but it's discrete number of eigenfunctions. But here, to deal with the more general aperiodic signals, we have to decompose the signal into a collection of. Still, it is infinitely many of these eigenfunctions, but it is more than the eigenfunctions that we have in the Fourier series case. Okay, because now omega is continuous, so you can have all the real line to index the eigenfunctions. But there we only have discrete numbers. So you can see that the underlying picture is the same, but we just, to deal with aperiodic signals, we just need more eigenbases in the Fourier transform. And then the inverse Fourier transform is, again, the same idea. So once we have this xj omega, which is the projection coefficients, right? So this is our signal xt, and we are by taking the inner product with the basis, eigenbasis, we are essentially, by projecting the signal of interest onto each eigenbasis, we obtain this capital X j omega, which is the coefficient, corresponding projection coefficient. So the inverse Fourier transform is also called the synthesis. But basically, once you collect all these different pieces of eigenfunctions and then linearly combine them to reconstruct your original signal. And from this picture, we can see that the signal of interest, the corresponding linear combination coefficient for a specific eigenfunction, it is exactly the Fourier transform given by the Fourier transform. So therefore, what this formula says is basically, for each eigenbasis signal, we linearly combine them. So that's why here we have an integration over omega. So we linearly combine all the eigenbases over the entire frequency domain. And for each eigenbasis, we combine it, use the corresponding coefficient given by the Fourier transform. Now, once you do this linear combination, you will end up with your original signal xt. And this 1 over 2 pi is just introduced to normalize. It's a normalization factor introduced to make sure this is a valid inverse. So we will see later in the proof. So I think to summarize, right, the underlying geometric picture of Fourier transform is exactly the same as the Fourier series. But the only difference is that now we are dealing with aperiodic signals. So we need to extend the eigenbasis from a discrete basis to a continuous basis. And if you look at the formula in terms of calculation, you just need to evaluate this integration. So this calculation is sort of similar to the Fourier series. So throughout this course, we will use this notation. So the xt, we use this capital F to denote the Fourier transform. So if we do the Fourier transform over signal xt, we end up with the corresponding Fourier transform, capital J omega. And on the other hand, if we start from this spectrum and do an inverse Fourier transform, which is denoted by capital F inverse, start with the Fourier spectrum, start with the Fourier transform, and we do an inverse Fourier transform, we will end up with the original signal xt. So this is Fourier transform, and the other direction is the inverse transform. Okay, we have a comment. This looks very similar to a Laplace transform. I think we will, after the Fourier transform, we will talk about Laplace transform. It is actually the Laplace transform is the generalization of the Fourier transform. Yeah, but it is developed based on the Fourier transform. Okay, and the other thing is that, again, both part xt, the signal, and this Fourier spectrum, the Fourier transform, both of these are complex value, right? The signal can be complex signal, complex value signal. Now you do that Fourier transform because the Fourier transform has this complex exponential. So again, in the end, in general, the spectrum is also complex value. So once we obtain the Fourier transform of the signal, we can visualize it by looking at this magnitude and phase separately, because in general it is very hard to visualize complex function. So we call the Fourier transform capital X J omega also the spectrum of the signal. Now this is standard, and to visualize this, usually in MATLAB, you can draw the magnitude spectrum by looking at only the magnitude of this spectrum. And also, draw another figure that visualizes the phase spectrum of this signal. So this is the magnitude, and this is the phase angle of the corresponding complex number. So everything goes back to our first lecture where we talk about the magnitude and phase of complex numbers. But in some special cases, sometimes you will find that the spectrum is a real value, and in that case, you can directly visualize the spectrum. Okay, so are there any questions regarding the Fourier transform? Yeah, I think the overall picture is the same as the Fourier series, but we are just extending the analysis tools to deal with aperiodic signals. And this is a list of Fourier transform pairs that you may utilize in the homework and also in the exam, the midterm or final exams. These are all given by these formulas. So we can look at some of them. The first line is exponential, where the signal xt is an exponentially decreasing signal, and this ut makes the signal causal. Right? So it only preserves the positive part of the signal. Now for such exponential decreasing signal, the corresponding Fourier transform is given in this way. So x capital X j omega is 1 over a plus j omega. So you can see that you can kind of imagine that the magnitude of this spectrum is decreasing as the frequency increases, which means most part of the energy of the signal, lies in the low frequency domain, low frequency region. And this is a two-sided exponential signal where we have it's basically doing a reverse of the first part and making the signal two-sided. Now for this signal, the corresponding spectrum is given in this way. Now the pulse signal is a rectangle signal between negative T1 and T1. It's negative T1 over 2 and T1 over 2 with amplitude 1. So it's a small rectangle signal. Now the corresponding spectrum is given by this sinc function, sine omega T1 divided by pi omega. So this later on we will see that this is a sinc function. And correspondingly, if the signal we are looking at is a sinc function, it's a sinc signal. So signal in the time domain looks like a sinc function. Then the corresponding spectrum is a rectangle spectrum. So these two forms a pair of Fourier transform. And the following are very special signals. Complex exponential signal is the corresponding spectrum is given by an impulse in the spectrum domain. And for sine and cosine signals, their spectrum are given by a pair of two impulses in the spectrum domain. For the impulse signal, the Fourier transform is given by a constant 1 in the Fourier domain. Okay, so all these pairs of transforms are derived by following the definition. Yeah, so next, so next we will go over some of these examples and calculate their Fourier transform by hand. So we can look at, so the first one I will leave it as an exercise for you. You can do it at home. So let's look at the second one. This two-sided exponential signal. So first of all, I write down the Fourier transform formula. The integration xt e negative j omega t dt. Now we are given that xt is e negative a times the absolute value of t, where a is a positive number. So the signal looks like this one. See illustrated in this in the top figure. So when t is greater than 0, okay, let's look at this signal. When t is greater than 0, we can get rid of this absolute value. So the xt is actually e negative a t, which corresponds to a exponentially decreasing signal. So that's the right-hand side. But when t is less than 0, when t is less than or equal to 0, the absolute value of t is equals to negative t. So this gives e times e to the power of a times t. Right. So the negative sign cancels out. And in this case, now it is a exponentially increasing signal. So we start from negative infinity, so exponentially increasing, and up to the original point 0. So the entire picture looks like this one. So it is an even function. It is symmetric with regard to the y-axis. Okay. Now we have the signal. We just plug it into the Fourier transform and do the integration. Because the signal is segmented, now we have a positive part, negative part. They have different expressions. So we are going to divide the integration into two parts. One is from 0 to infinity, where we have e to the power of negative at times e negative j omega t. And the other part is negative infinity to 0. Well, in this case, xt is given by e to the power of at. So we don't have a negative sign here. See, that's the difference. And then still we have e to the power of negative j omega t dt. Okay, so these two integrations are standard integrations over complex exponentials. So we just do the calculations carefully. So it looks like here, so we have negative a plus j omega t dt. And here we have a minus j omega t dt. And this gives e negative a plus j omega negative a plus. So it's this one evaluated at 0, infinity plus this one. Right, the standard calculation. Okay, then we just plug in these values. So now here we need to be a little bit careful. So this is replacing t by positive infinity. So we have, okay, we have this one, e to the power of negative a plus j omega infinity minus. Now this one's replacing t by 0, which gives 1. And similarly, here we have 1 minus e to the power of a minus j omega times negative infinity. So my question is, what are these two numbers? What are these two numbers? Looks like they are not determined. Now, the first one is e negative a plus j omega t limit t goes to positive infinity. Now here's my question: what is this limit? Does this one has a limit? Like, because here in the exponential part, this is a complex number. It goes to and then multiplied by infinity. So what is the corresponding limit?
Zero.
Why is it 0?
I think the limit goes to 0 as the signal goes down towards 0. I'm not
Yeah,
sure how else to explain it.
But here is a right. This is a generally complex number, right? So you need to look at the both. So when you say the signal goes down, so you can see that if we look at negative e to the power negative t, and let t goes to positive infinity, then this is 0, because we know that this is a real number, and as t increases, this number decreases. In the end, it goes to 0. Now this is clear. But here we are looking at a complex number. So the answer you mentioned was correct, but is there a formal, more rigorous argument? Like when you say the signal goes down, are you looking at its amplitude or its phase? Yeah,
I was looking at the magnitude.
magnitude, right? Yeah, that's the right idea. So basically, you look at you decompose this part into this one. Now this is a standard polar form of complex number, because this is a real number, and this is a standard complex exponential. So for this complex number, the amplitude is given by e to the power of negative at, right? The amplitude is a real number, positive real number. The phase is given by negative omega t. So we can see that both the amplitude and the phase are time varying. However, since a is positive, and if we let t goes to positive infinity, it is clear that this part will goes to 0 as t goes to infinity. Which means the amplitude, the magnitude part goes to 0. The phase part, it does not converge, because omega is a constant. Negative omega t, if t goes to infinity, the phase also goes to infinity. So this part does not converge, but that's okay, because this part is always bounded. No matter so the phase part is no longer important when the amplitude of the signal vanishes, right? The amplitude of signal vanishes means that the signal has no energy, it simply disappears. So as long as the amplitude, as long as we can argue that the amplitude goes to 0, so the signal will go to 0. So you conclude that this is 0 because the amplitude goes to 0. And similarly for the second part, you can do the following the similar argument. The amplitude is given by e to the power of a times negative infinity, also goes to 0 because a is a positive number. So this is also 0. So we just ignore these two parts. And then this gives us a very simple result, which is 1 over a plus j omega plus 1 over a minus j omega. And because these two, they have the denominators, they have a special structure because they are conjugate to each other. So you can do a further simplification. So you find out the common factor. So this becomes a minus j omega plus a plus j omega. And then here you get 2a. And in the bottom, you have complex number times its conjugate. So it's basically the square of the magnitude. So this is the spectrum. And magically, you can see that this spectrum is a real value spectrum because it does not have a j as that complex unit inside. Every j disappears magically. So in the end, we can visualize this spectrum in one figure. We don't need to plot the amplitude and the phase because the phase is always 0. So by plotting, and you can see that this function in terms of omega, it is some constant divided by a constant plus omega square. So this is an even function that looks like this. The bottom part. So this is the spectrum of this two-sided exponential signal, and we can see that again, most energy of the signal is concentrated in the low frequency region, which means that this signal is relatively, it's a low frequency signal.
What did you say about the phase?
The phase, okay, since the spectrum, entire spectrum is given by this one, and this is only a real number, right? Because a is real, omega is real, so this is a real number. So the phase is simply 0. Because any real number can be written as b times e j ej times 0. So for real numbers, the phase is actually is simply 0.
Right, gotcha.
Oh, actually, yeah, I should be okay. I should be more rigorous. So this is actually a positive. The amplitude, sorry, the spectrum is actually all positive because we know that a is given as a positive number. A is given as a positive number. A square, omega square, they are all positive. So in the end, the entire spectrum are all positive numbers, real numbers. So for all positive real numbers, the corresponding phase is 0. If these real numbers are, some of them are negative, then the phase should be pi instead of 0. So the phase can change the sign of the real numbers. But in this case, this is always positive. So the phase is always 0. Yeah, so in this case, we can simply visualize this in one figure, only looking at its amplitude, magnitude. Okay, so this is the two-sided exponential. So this verifies that table, the second row of this table. And you can see for all the calculations, it's basically integration, And we have this example 2 is about Fourier transform of the impulse function. For this one, you follow the same idea. I will just sketch the proof of this one. So this impulse, the pulse function is given as a small rectangle between T1 and between negative T1 and T1, and the amplitude is 1. So because it is the signal only occurs within this window, so the integration is between negative T1 and T1. And now within this window, xt is constant 1, so it's 1 times e negative j omega t dt. So this is the Fourier transform. And then we do the integration. So very quickly we have this result, and then we end up with this one. And for the numerator, you can look at the inverse, Euler's formula, because here we have a pair of complex exponentials that are conjugate to each other. So this reminds us of the inverse Euler's formula. Check the inverse Euler's formula, you will see that this entire thing can be simplified to 2 times sine omega t1 divided by omega. So this is the result. So again, very interestingly, this spectrum is, again, it's a real numbered spectrum. It is not a complex value spectrum. So we can visualize the spectrum of in this figure. And this is essentially a sinc type function, because we can rewrite it in this way. It's 2 times sine again divided by T1 and multiplied by T1. And then let's go back to the definition of the sinc functions here. The sine pi t divided by pi t. And here, so by comparing this one with the definition, I think this is sinc function evaluated at. So we let pi t equals to omega t1, we get t is omega t1 divided by pi. So this is xj omega. So you can see that xj omega is a constant times this sinc function. And for this sinc function, it is actually subject to a time scaling. Sinc omega, and then we do a time scaling with factor t1 over pi. So in the end, after these basic operations, the shape still looks like a sinc function. So it is the spectrum still looks like this one. And again, you can see that most of the energy is concentrated in the low frequency region. Okay, so this is example 2. Example 3 is another pair of sinc and the rectangle function. But now we are given a signal whose spectrum is a pulse function. The spectrum is a rectangle in the spectrum domain. And then we can use the inverse, given this spectrum, we can use the inverse Fourier transform to find out the original signal, xt. And following the inverse Fourier transform formula, this is the inverse Fourier transform. Okay, so you do the same thing, do this calculation, you end up with this signal. So which means that if you look at this signal, again, this signal is a sinc type signal. So if you visualize the signal, it looks like this one, the sinc signal. So such a signal has a rectangle spectrum. Okay, so the entire spectrum of this signal is limited within a limited band. So we call this signal a band limited signal. The spectrum is within a limited band. Okay, and this shows that this two has a perfect duality. If the signal is rectangle in the time domain, the spectrum looks like sinc function. If the signal looks like sinc function in the time domain, the spectrum looks like a rectangle. So they form a pair of Fourier transform. So from now on, you should be sensitive to these two types of signals. Right? If you see a rectangle in either time domain or the frequency domain, always remind you that this is related to the sinc signal in another domain. Okay, so these are all the examples, and you can work on your own to figure out the rest of the pairs of transformations. So next we will talk about the properties of Fourier transform, and this is probably the most important part for the Fourier transform, because for most of the time we will utilize these properties of Fourier transform to avoid calculating doing those complex calculations directly. The first theorem is the duality theorem, which is a generalization of the two examples that we just visited. It says that if the signal xt has a corresponding Fourier transform given by capital Xj omega, so these two are two functions in the time domain and in the frequency domain respectively, and they form a Fourier transform pair. If we can obtain this spectrum from this signal, then if we look at if we start with a spectrum that is given by if we start with another signal, xt, capital Xt, and this capital Xt is given by the spectrum here. If we start by replacing j omega with t, right? So basically you copy this spectrum and make it a signal. So if we start with this signal, then the corresponding spectrum is actually related to the original signal. So it's 2 pi times small x evaluated at negative j omega. And this explains the previous two examples that we just saw. But we start with a rectangle signal in the time domain, and we figure out that the corresponding spectrum is a sinc type spectrum. But now in the next example, we show that if we copy this spectrum and make it a signal, so consider now a sinc type signal in the time domain, then the corresponding spectrum looks like the previous signal. And it is actually taking the previous signal and doing a time reversal and scale by 2 pi. But in this case, because the signal is an even signal, so doing a time reversal does not change the signal. So it is still a rectangle signal, a rectangle spectrum. Okay, so this is duality. And here are more examples. If the signal is impulse signal and following the Fourier transform, you can find out that the corresponding spectrum is given by constant 1. So which means that such an impulse consists of all types of eigenfunctions in the frequency domain. So the spectrum spans over the entire frequency domain. And now we copy this spectrum and make it a signal. So consider a constant signal, xt, and then you can following the Fourier transform. You will see that the corresponding spectrum is given by an impulse. It's 2 pi times delta omega.
Where does the 2 pi come from in that?
I believe intuitively it comes from the inverse Fourier transform. We have a 1 over 2 pi here. Yeah. So somehow you will do a reversal and make it 2 pi. Yeah. If you move 2 pi to the left hand side, you have 2 pi times xt, right? I think that's why we have 2 pi here.
I see.
And the other properties are very similar to the properties of Fourier series. But let's visit them here one by one. Linearity is very simple, so I will skip this one. If you can linearly combine two signals, the corresponding Fourier transform, the spectrum is also linearly combined, because the Fourier transform is a linear transform. Time shifting is very, very important. It says that if a signal has a Fourier spectrum capital X j omega, then for this time shifted signal, the corresponding spectrum is given by the previous spectrum x j omega multiplied by this complex exponential e to the power of negative j omega t naught. So you can see that the time shift in the time domain will cause a phase shift in the frequency domain. Right, because this complex exponential, basically it will modify the phase part of the spectrum, xj omega.
Is it possible to do an example of the time shifting for this?
Sorry, you want I didn't get it. Do you want an example for this?
Yeah, is it possible to do an example of the time shifting?
Yeah, we can actually prove it. Yeah, let's actually prove this relation based on the definition of Fourier transform. So we have xj omega t is the Fourier transform of xt, right? And now we are looking at, let's call yt is a shifted version of xt. And now let's look at yj omega t, sorry, yj omega, which is, xt is the yt times e negative j omega t. Right. So this is the Fourier transform of yt. We want to look at the Fourier transform of yt and then relate this Fourier transform to the Fourier transform of xt. So if you compare these two integrations, you can see that the difference here is t versus t minus t naught. So this motivates us to consider a change of variable. So if you do a change of variable, t prime equals to t minus t naught. So, and with this, yj omega now becomes xt prime e negative j omega, and t becomes t prime plus t naught, and dt is dt prime. And then you can see you kind of have this constant coefficient, constant complex exponential part, and you can take it out, which gives you this phase shift. And the rest of the part is xt prime e negative j omega t prime dt prime. Right, and this part is exactly the same as xj omega. Okay, except for a change of notation. So this is xj omega actually. So this shows that the spectrum of this yt is given by the spectrum of xt multiplied by this phase shift operator. Right, so it applies to any functions, and you can see that the underlying idea is a change of variable of integration. And this is an application example. So from that table, we know that this two-sided exponential has this spectrum. So therefore, if we want to derive the spectrum of this shifted two-sided exponential, we don't have to go over the definition again. Just applying this time shifting property. So after this time shift, the spectrum is given by the original spectrum here multiplied by the phase shift factor. And that's it. And now you can see that a shift in the time domain will modify the phase. So in the end, the entire phase spectrum is shifted. So the phase is shifted by negative omega t naught, by the constant negative omega t naught. Okay, so whenever you see a signal that has a time shifting as a time shift inside, you can think about the time shifting property of the Fourier transform. And the next property is kind of a duality of the time shifting properties called the frequency shifting property. And this is again very extremely important. These two are probably two of the most important properties of Fourier transform. So we have this original pair of Fourier transform, and then if we look at these signals, xt original signal multiplied by this complex exponential signal, multiplied by e to the power of j omega naught t. Here, omega naught is any frequency, any fixed angular frequency. So it is like now you are modulating your signal by a complex exponential signal, right? Here, modulating means that you are multiplying xt by e to the power of j omega naught t. For this signal, the corresponding spectrum is given by taking the original spectrum and shifted in the spectrum domain by omega naught. Therefore, this means that a modulation in the time domain, a modulation by complex exponential signals in the time domain will cause a frequency shift in the spectral domain. And let's look at, okay, I think we will visit these examples in the next lecture, but the application of this frequency shifting properties is very important. Basically, if you want to send out a voice signal through the wireless communication channel, we know that the voice signals, when we speak, the voice signals they lie in the low frequency region, because I think the maximum frequency that human can generate, is, for example, is 44K hertz. 44. I forgot it's 20K hertz, if I remember correctly. But anyway, our voice are relatively low frequency. However, if we transmit low frequencies signals through the air, the signal will be attenuated significantly. So the solution is to, before we transmit the signal, we raise it to, we shift the signal in the frequency domain to a much higher frequency. And then that higher frequency signal can be easily sent through the air, open air. And the way that we do this is simply, through this frequency shifting property. We multiply our voice signal xt by a very high frequency complex exponential signal, ej omega naught t. This omega naught is angular frequency. You can design it, but usually it is much higher than our human voice. Once you do this modulation through this frequency shifting property, we know that this is equivalent to moving our signal in the spectrum domain from a low frequency region to a much higher frequency region. And that's why we can transmit our signals reliably through the open air. So we can talk more about this in the next lecture. And by utilizing this frequency shifting property, you can verify the following examples. Okay, so I think I will stop here today, and we'll see you on Thursday. And I will be in the office hour later on. Okay, I'll see you guys then.